Okay, so last time we talked about limit theorems in the classical and the free world. We started with the central limit theorem, but then we looked also more general ones. And one reason for this is that it really shows us how classical and free probability theory goes in parallel. And so maybe let me recall the result from last time. This was somehow the basic limit theorem. Okay, so just recall. So what we are doing is we want to write variables as sums of many small independent or free variables and see what is the distribution of this if the number of summands goes to infinity. So we assume we have A and I. Okay, so n is the number of summands which we have. We want to increase this. And for each n, we have n many summands, so I is running from 1 up to n. And those guys, so these A and I, they were for each n classically or freely independent. And then, we were looking somehow on the distribution of an1 plus an2 plus and so on up to an and want to understand that this converges to some limit distribution A. And the assumptions are those guys are for fixed n are classically or freely independent, and then of course I must make some assumptions on their distribution. In particular, for different n, I mean they must be related somehow. And the assumption which we made was the limit n times the moments of these guys here is scales essentially this 1 over n. So it is the phi of a n I. So they are all identically distributed, so it doesn't depend on I. And then I take the rth moment that this moment goes essentially like scales with 1 over n. So this times n in the limit is something, some number which might depend on the moment. Okay, and then we calculated what is the distribution in the limit. And it turns out there is a limit distribution, and we get a nice formula for this. And again, it shows that in the classical and the free case, we get essentially the same structure of the formula. The difference is just that in one case we are summing over all partitions, in the other case we are summing over the non-crossing ones. Also, the result was phi of ak, the limit, let's say, kth moment, that this is given by a summation over all partitions of k elements, and the contribution of such a partition is in terms of those kappas, but it's a multiplicative contribution, namely it's a product of kappas, where for each block of pi I get a kappa where the index is given by the number of blocks, the number of elements in the block. Also, it's a product. It's a product over the blocks in pi. So one factor for each block. And what is the factor for the block V? That's the kappa, but the index is the number of elements in it. Okay, and that's the classical case. And if I'm in the free case, I just have to replace all partitions by the non-crossing ones. Right? It's the same formula. Okay, so this means we get here elements which are given in a nice way in terms of this formula. But maybe the main information which you see at the moment is really this parallelism between the classical and the free world. So we have limit theorems in the classical world, and we have corresponding limit theorems in the free world, and the result is on a structural level very similar, and it's really just replacing all partitions by non-crossing partitions, if you go over from classical independence to free independence. Good. Okay, so let us look a little bit more on this. Maybe put the free central limit theorem in this formula, and maybe also understand the case of the Poisson distribution a little bit better, because this was the one which I used as motivation for looking on such general limit theorems. Good. Okay, so this is maybe a remark or examples. This was 217 remarks. down the structure of this formula for small k, let's say. And of course you see, I mean, we are summing over non-crossing partitions in the free case, and in the classical case we get additional terms. So there will be more terms in the classical case, but otherwise it's the same. Okay, but so maybe second part of this relation, maybe let us look at the central limit theorem. So the central limit theorem should also be contained in this. I mean, this is a more general limit theorem as the central limit theorem. And so how can you recover this? So in the case of the central limit theorem, those a's here in our sum, they were actually very special because they were a normalization of one given distribution. And the normalization was by a factor square root of n. So in this case, we have the a and I. This actually is given by one variable ai, and then we just scale depending on n. The scaling was the square root. Because there we were looking on a1 plus a2 up to plus an divided by square root of n. And if you want to write it in this form, then of course those guys here are just given by this. Good. Okay, and then in this case, we can see that all those limits exists, and we can also see what they are. So maybe what is kappa 1? So kappa 1, so this is the limit, n going to infinity. I should take n, and I should multiply it. Okay, kappa 1 means I should take the first moment, so I should take phi of this guy, but this is phi of ai, divided by square root of n. Okay, and of course, this is 0, because in the central limit theorem we assume that the first moment is 0. Because otherwise we would have problems, because this would not have a limit. Okay, so this is 0, since the usual assumption in the central limit theorem is that the first moment is 0. Then what is kappa 2? Kappa 2 is the limit n going to infinity, n, and then I multiply with the second moment of this guy, but of course this is then the second moment of ai, and I'm dividing by the square of the square root, so I'm just dividing by n. So I have phi of ai squared divided by n. Well, and now you see, of course, that's exactly the right order, it survives, and we normalize the second moment in our central limit theorem to 1, so the contribution of this is just 1. Because the second moment was normalized to 1. Okay, and the higher ones, of course, they are dividing by a higher power of n, and so this also will go to 0. So I'm looking on kappa r for r bigger than 2. So this is the limit. N to infinity, I multiply n with the arc moment of those guys, which is the arc moment of ai to the power r, and then I'm dividing by n now over 2. But if now r is 3 or 4 or higher, then of course this here goes faster to infinity than this, and the whole thing will go to 0. So this is equal to 0 if r is greater or equal than 3. Okay, and so this means we recover the central limit theorem, because in this formula here, I mean, we are summing over all partitions, but then what is the contribution of a partition? I mean, it's a factor for each block, but the factors are 0 unless the block is a pair. So this means if I don't want to get 0 here, every block should be a pair. And this means it should be a pairing, and then I just multiply once, so the contribution of the pairing is 1, and the contribution of everything else is 0. And that's exactly the formula which we had in the central limit theorem. I mean, it looked exactly like this. The only difference was that here we are summing over the pairings. I mean, all pairings in the classical case, and the non-crossing pairings in the free case. And of course here we have the factor of just 1. Okay, so get here is exactly the result of our free central limit theorem. formulas in our general limit theorem. So, 16, they really give us the classical and the free central limit theorem, which was 2.7. Good. Okay, so we see that the free central limit theorem is contained here. And actually, I mean, so this, we proved this theorem, so actually this gave maybe even maybe more direct or even faster proof of the classical one. Of the central limit theorem. Okay, but now maybe let us look another important limit theorem, maybe the other important distribution one knows from classical probability theory, which is the Poisson distribution, which also comes out from a limit theorem. And I told you what is the limit there. There it was that all of these couples here, they are independent of R. In the general limit theorem, we allow that, I mean, the limit of this guy for the last moment is a number which depends on R, but in the Poisson situation, this number is independent. So we said it's always lambda, and maybe you can even take lambda equal to 1 as a normalization. And so let us look what we get there, because in the classical case we should get the Poisson distribution, and then of course in the free case we should get a free envelope. So in the case of, let's say, rare events, that was the limit theorem for the Poisson case, and let's say I take this intensity T lambda equal to 1. So what do we have? I mean, this was in 214, we talked about this. The kappa R's, which is the limit n going to infinity, n times, and then all those moments here actually were 1 over n, or in general lambda over n. That was a distribution where this a and I had a distribution, they have the probability 1 over n for taking on the value 1, and 1 minus 1 over n for taking on the value 0. Okay, so they have this moment. And in this case, I mean, there's actually no need for taking the limit. This is exactly 1 for each n. So the limit of course is then also. So this means in this case, all the kappas are just 1, and then of course what do I get with the sum? Then it's again just a counting problem, because now independent of which pi I take, I always just multiply once here, so each of them will give the contribution 1. And this means the sum here is just counting the number of all partitions or of non-Poisson partitions. Here, in our general limit theorem, this gives, in this case, that the A kth moment, let's say the classical version of it, that this is just given by the number of all partitions, and in the corresponding free case, free version in the limit, this is just given by the number of non-Gaussian partitions. Good. Okay. And so what I'm saying here is essentially, in the classical case, we know what the limit is, and this is the Poisson distribution. So actually, I'm saying here that the moments of the Poisson distribution are given by the number of all partitions. Yeah? And this is indeed the case. Maybe that's not what we usually learn when we are talking about the usual Poisson distribution, but in principle, from this point of view, I mean, why is the normal distribution so important? Because it's the limit. It's a limit in the central limit theorem, and so why is this? Yeah, what is the relevance of the normal distribution? Its relevance is that its moments are given by counting the number of pairings. And why is the Poisson distribution so important? Because its moments are counting the number of all partitions. And now, of course, we have the analogs here. So maybe Okay, so let me first say, of course, indeed, those are the moments of the classical Poisson. Okay, maybe this is not obvious, but I mean it will be one of the assignments, so it's somehow not too hard to prove, but maybe you really should think about it, because that's, yeah, usually you don't hear about this when you learn in probability theory about the Poisson distribution. But indeed, this is the case. So the moments of the classical Poisson distribution, and we are talking here about the parameter 1. And then, because then it's a counting problem. So you see, if the parameter is not 1 but lambda, then you will get here powers of lambda, and you will get different powers of lambda depending on the number of blocks which you have. Okay, so for different lambda, it's not just a scaling of the Poisson, but it's really a different one where you're counting here a little bit different. Okay, but for lambda equal to 1, it's really just a counting problem. Parameter 1. And maybe I say it again. So this is the Poisson distribution. Of course, you can write it down very explicitly. There are explicit formulas for the Poisson distribution. So the Poisson distribution is a probability distribution on the numbers 0, 1, 2, 3. So just on the positive integers, non-negative integers. And so the probability of number p, this is just 1 over e times 1 over p factorial. In general, there was also power of lambda. And you see, I mean, this is a probability distribution because the sum over 1 over the factorials is just e. So this is the normalizing factor, which makes it a probability distribution. Okay, here we are saying that the moments of this guy here are actually given by the number of partitions of k. No? Okay. Or explicitly, so this means, so what are the moments of such a probability distribution? I'm summing over p from 0 to infinity, the kth moment, so I'm taking p to the k, and then what is the probability of p? This is 1 over e times 1 over p factorial, and I'm claiming this is the same as the number of partitions of k elements. Okay, this is not totally obvious, but it's also not so hard to prove, right? If you really want to prove this, and you will want it in the assignment, then it should be straightforward. Good. Okay, so this means, I mean, again, it's the case that those are actually natural numbers. I mean, if you just take the Poisson distribution, you calculate the moments, you get natural numbers, but there's a priori no reason why it should be. But this tells you why it should be, because they are numbers which actually count something interesting, and they also have a number, they have a name, namely those numbers are called the Bell numbers. So, the number of pk, so is a sequence of numbers, they are called Bell numbers. Okay, in contrast to the numbers which we had up to now, I mean, you can write down nice recursion formulas, but there's no nice explicit formula. Okay, so there are many ways of describing them. For example, they satisfy nice recursions. Like Catalan numbers satisfy nice recursions, but in Catalan numbers we can really write down very explicit solutions for this recursion, but here there is no nice explicit solution in terms of binomial or something like this. Okay, nice recursions, but there are no explicit formulas. Okay, maybe let me write down the first few of them. So what is the sequence? So 1, that's for p for k equal to 0. Then 1 is for k equal to 1, and then it's 2, 5, 15, 2, 1, 3, 877, and so on. Oh, okay. So those are numbers of elements in P of k, but it's also the moments of the Poisson distribution. Oh, so I mean, this is the mean of the Poisson distribution. This is 1. This is the second moment, the third moment, and so on. For example, this here is the 7th moment. So it's the 7th moment of the Poisson distribution, but it's also the number of elements in the number of partitions of 7 elements. Good. Okay, so that's about the classical Poisson. And in assignment you will think a little bit about this. But now, of course, I mean, the same way as the free analog of the Gaussian distribution is very important and deserves its own name. We also should, the analog here in the free world is also important, and we should understand a little bit more about it. Maybe first also give it a name, and we call it, of course, just the free Poisson distribution. In the classical context, I mean, the analog of the Gaussian or the normal distribution is not called the free normal or the free Gaussian, but it's called semicircle because actually this distribution appeared before in different contexts, and it also has a nice semicircle form. It could also be called a free normal distribution, but usually it's a semicircle. But here in the Poisson context, I mean, we just put the adjective free. So here's our definition. And then we try to understand it a little bit better. And again, I mean, what we get here in classical, usually the case, there are moments of a probability measure, so there's some positivity in the background. Also, usually we require that elements which have those moments, they should live in a star probability space and they should be self-adjoint. So A phi, our non-commutative probability space, should actually be a star probability space. Which means that there's also a star, and then of course the phi should be positive, and then random variables usually are self-adjoint, so self-adjoint random variable, let's call it x, it should be self-adjoint, so x is the same as x star, random variables are elements in our algebra, so such a guy is called a free Poisson element. Free Poisson element, random variable. And, okay, we can also take a parameter there, like in the classical case. So with parameter should be a positive number. Yeah, if its moments are given by this formula, and all the couples are just lambda. No? That was like it was for the classical Poisson with this parameter lambda. So if its moments are of the form phi x and k is given by sum over pi, which are now non-crossing partitions. For a classical Poisson, I have sum over all partitions. And what is the contribution of each of them? It's a product of lambdas, and I get a lambda for each block. So it's just lambda to the number of blocks. Number of blocks. So you see, it's not just a scaling of x with lambda, but it's really, I mean, because I mean, we have something here over pi's which have different numbers of blocks. Okay, so this is not just a counting problem. But if lambda is 1, of course, it's a counting problem. So this is the particular case. Before, so in particular, 1, we have at the moment, our free Poisson parameter 1 is just given by the number of non-crossing elements. Of non-crossing partitions of k elements. Good. Okay, so this is just a name for this object, but again, we should try to understand it. In particular, can we give an explicit distribution? I mean, as for a semicircle. First, I mean, you could say a semicircle is something whose moments is given by the number of non-crossing pairings, but then, I mean, we really can present a nice distribution which has those moments. So maybe the first thing would be to understand actually what is the analog of the band numbers. I mean, what are those numbers? So what are the free band numbers? And actually, it turns out that the situation here is quite a bit different than in the classical case. I mean, in the classical case, the band numbers are really something different from the numbers of elements for pairings. Because I mean, the number of pairings, this was these double factorials, and the band numbers is something which are totally different numbers. But in the free world, it turns out that there is quite a remarkable relation between all non-crossing partitions and all pairings. Because essentially, it's again the Catalan numbers which show up here. So, actually no new, I mean, there are no free band numbers in this sense, it's just the Catalan numbers. So what are the free band numbers? Actually, so it turns out, this has a very simple and trivial solution. It turns out we have, we would call it free band numbers, namely the number of non-crossing partitions of k elements is actually the same as the number of non-crossing pairings of 2k elements, which of course are the Catalan numbers, ck. So the number of non-crossing partitions of k elements are just again the Catalan numbers. So in particular, it's something for which we have a very explicit formula, in contrast to the classical band numbers. So we have here the Catalan numbers again. Maybe I should show this. And this is again something which is, okay, maybe also not totally clear, but it's also quite straightforward to prove, and it will also be a part of the next assignment to prove this. Good, but so let me just make this a little bit clear. Because here we see another interesting phenomenon in free probability theory. I mean, it's many things go parallel to the classical situation. So you're replacing, I mean, we get the same structure of the formulas. You replace all partitions by non-crossing partitions. But actually, in the free world, there are more relations between objects. So I mean, there are, by some coincidence, by some non-crossing reason, I mean the non-crossing partitions and the non-crossing pairings, there's a bijection between all partitions and all pairings. There's no bijection. So this means in the free world we have somehow relations which we don't have in the classical world. And of course this also has some probabilistic consequences. So there are statements in the free world for which you don't have classical analogs, which of course makes it interesting. So the free probability theory is not just the one bijection of the classical probability theory where you just can give a bijective version of everything which you have in the classical world. You can give a bijection of many things, but there are also other things which are not there in the classical situation. Okay, so maybe let me look on this. So for example, in the free world we have the NC of k, so I'm claiming, and this is in bijection to NC of 2k. So the number of elements there is the same. So maybe let us look on this for small k, just to make this clear, and also maybe then look on the analog in the classical world. So for k equal to 1, so what is a non-crossing partition of one element? Of course there's only one, the one which has a symbol. So here we have 2k, so this, and of course here I should take the pairings. So I I'm taking pairings of 2 elements, and there's only one pairing in this one. So the number in both cases is the same. So for k equal to 2, so here I'm looking for non-crossing partitions of 2 elements, and there are 2 of them. And there's the one which only has one block, and then there's the one which has 2 blocks. Okay, here I'm looking for the non-crossing pairings of 4 elements, and again we know that there are 2. So there's this one, and there's this one. In those cases there are 2. And of course this is the color. Okay, for k equal to 3, so what are the non-crossing partitions of 3 elements? There are 5 of them. This one, this one, this one, this one, this one. So there are 5. And we know that we also have 5 non-crossing pairings of 6 elements. So we move this one, this one, this one, this, and this. Oh, this is the 5 non-crossing, and so on. And then, I mean, if I go to the next, we have 14, the next Catalan number. So we have 14 non-crossing pairings of 8 elements, and we also have 14 non-crossing partitions. Because I mean there are 15 partitions of 4 elements, 3 times 5, and one of them is crossing, so there are 14. Okay, so you see we have really here always the same. But in the classical world, of course, this is not true anymore. Even for small numbers, we start to differ. So what we see here, this is very different from the classical world. There I can count the number of partitions, I can count the number of pairings, but I'm getting 2 different sequences of numbers. So pk, and here p2, 2k. So the numbers, different numbers. Of course, for k equal to 1, it's still the same. I have one pairing of 1 element, and I have one partition of one element, and I have one pairing of 2 elements. So here both the same. But even for k equal to 2, we already see a difference. Because I'm taking here the partitions of 2 elements. Of course, this is still the same as for the non-crossing, because there's no difference. So I have those 2 guys. But here, now I'm taking the pairings of 4 elements. And of course, there's one more than in the non-crossing case. Because I'm here, I have the crossing pairing. So I have the non-crossing ones. But in addition, I also have the crossing pairing. So actually here I have 3. You see, I'm starting to get a difference here. And then if I go further, I mean for k equal to 3, I have the 5. I mean, I'm still, for k, the number of all partitions of 3 elements is still the same as the number of non-crossing. Because for 3 elements I can see a crossing. So here I still have 5. Yeah, but here, what are the number of pairings of 6 elements? So this is 5 times 3. So here I have 15. And then if I go on, I get 15 here. And of course we know we have 14 non-crossing ones, and there's one more. So this is 3, this is 4, and here we get 105, and so on. Okay, so those are the numbers of all pairings, which is given by 2k minus 1 double factorial. Okay, and those here are the bad numbers, for which we don't have an explicit formula. So it's just a different sequence of numbers. Good. Okay, so we see that here really, I mean, somehow this property of being non-crossing is a quite rigid structure, and it means that within non-crossing partitions, there are many bijections for which you don't have classical analogs. Okay, and so this coincidence between the number of non-crossing partitions and the number of non-crossing pairings has of course then also some probabilistic consequence, because actually we can now relate the free Poisson element with a semicircular element. Because what this actually says is that the square of a semicircle is a free Poisson. Work this out, and of course this is very different from the classical one. I mean, the square of a normal or Gaussian variable has nothing to do with the Poisson variable. This coincidence, this implies that the square, let's say S squared, of a semicircle, that's the standard semicircle. So standard semicircle means the second moment is 1, and the moment, we know the moment of this are given by counting the non-crossing pairings. And I'm saying here the square of such a guy is actually free Poisson is lambda equal to 1. And I mean, this is obvious, because I mean, for a free Poisson is lambda is equal to 1, I need a variable for which the kth moment should count the number of non-crossing partitions of k. And I'm saying, of course, that's what the kth moment of S squared is doing, because kth moment of S squared is the same as the 2kth moment of S, and if S is a semicircle, we know that this counts the number of non-crossing pairings of 2k elements. So this is the same as the non-crossing pairings of 2k elements, but now we know that this number is actually the same as the number of non-crossing partitions of k elements. And that's what we want from free Poisson. And of course, if S is several joint, then S squared is also several joint. So this means we have here really the strange thing that there's a relation between a semicircle and Poisson, which of course in the classical world there's no relation between a normal variable and the Poisson variable. In particular, a normal variable has a nice continuous density, and the Poisson variable is a very discrete thing. Okay, and this relation here, of course, also allows us to write now down a very explicit form for a distribution which has this property. So like the semicircle. I mean, for the semicircle, we could write down a probability measure which has those moments. But because of this connection, we cannot also write down the density for a free Poisson. So density squared, so our free Poisson is S squared. We know the distribution, the density of S, so we just have to rewrite this as a density for S squared. So what is this? So phi of S squared to the power k, which is the same as phi of S to the power 2k. Of course, S has a semicircle distribution, so we know that this is the same as the 2k moment t to the 2k with respect to the semicircle distribution, which has a density 4 minus t squared dt, and some normalization factor 1 over pi. Okay, and now, of course, we want the kth moment, so we should write this as the kth moment of something. And of course, we do this by a change of variable, by going over to the square, but of course, this interval, this is not 1 to 1, so we should split this here into the interval from -2 to 0 and the interval from 0 to 2. And both give the same contribution. So this here is of course the same as 2 times this integral, where I just go from 0 to 2. Because going from -2 to 0 gives the same contribution, because here everything is in squares. So I have here t to the 2k minus t squared dt. And now I can make a change of variable, namely now I call x squared equal to x, so that I get here x to the k, so I really get the kth moment of something. And then of course the dx is the same as 2 times t dt, and I'm just plugging this in here. So what I get then is, so this is 1 over pi, so I have here 1 over pi, I have integral, I'm going from 0 to 2, but in terms of x, then I'm going from 0 to 4. 4. T to the 2k is now x to the k. The square root is 4 minus x squared. And 4 minus x. T squared is x. And dt, this is dx divided by 2. And the t is the square root of x. Divided by 2. T is the square root of x. Okay, so you see what you get in the end is 1 over 2 pi, so here's 2, integral from 0 to 4 x to the k, and for this my density here, it's 4 minus x, here's also square root, so I bring it under the square root, if we divide by x, so it's 4 divided by x minus 1. So you see that for the free Poisson, we get a density of this form. So in particular, we also get a continuous thing, which is very different from the classical Poisson. So I mean, it is even more mysterious why this guy should be the analog of the discrete Poisson if you look on it from the analytic point of view. Right? I give you just the densities of those two guys, and I'm telling you that one is the free analog of the other. From these formulas, this wouldn't be clear at all. No? But from the point of view that those are the distributions which counts all the partitions, or all non-crossing partitions, I mean it's very clear why they should be analogs to each other. So maybe we just draw the distribution. So this is a distribution which lives on 0 to 4, and it has a density, this square root of 4 over x minus 1. So it looks somehow like this. So it goes to infinity here. So this is the square of the semicircle distribution in this sense. But this is the free distribution for lambda and maybe later we will also look on different lambdas, but that's the one which you can do at the moment very easy. And maybe you should contrast this with the classical situation. So the classical Poisson. I mean, what is the classical Poisson? I mean, this is something which lives just on the integer numbers, the positive ones. So it lives on 0, 1, 2, 3, and so on. And it has a probability there. And I mean, actually, so let me draw these probabilities like this. So I put somehow something like this. So this height is actually a 1 over e. So this is the classical Poisson distribution. Again, 1 equal to 1, for which the probability of the value p is 1 over e times 1 over p factorial. form. Also for p equal to 0, this is 1 over e, this is also 1 over e, then this is 1 over e divided by 2, and then it's 1/6 of this, and so on. So that's the classical Poisson distribution for this parameter. Alright, okay. I mean, those two distributions, they are analogs of each other. That's the free Poisson and that's the classical Poisson. They are looking in analytic terms will be different. Okay. And in particular, in classical probability theory, there's also no relation between this guy and, let's say, the square of the normal distribution. And then, of course, the square of the normal distribution also has a continuous density. Of course, it has nothing to do with this. Classical probability, there is no relation between the square of normal variable and the Poisson variable. Good. Okay, so this gives us some idea about the general relation between classical and free. So there's a lot of structural similarity replacing all partition by non-crossing, but there are also surprises you should expect in the free world, because there can be more relations there which we don't have in classical world. Or maybe sometimes it could also be the other way around. Maybe in classical theory we have statements for which there's no free element. Good. Okay, but maybe one final thing which I want to do in this chapter here is maybe to see what else we can get from the structure of the formulas which we get in the limit of our limit theorems. So I mean, you might say, okay, it's nice to get the limit theorem variables, which can be written in this form that we are summing over all partitions, and then we multiply some factors kappa to give us those moments, but it might not be so clear what this tells us in general about freeness itself. Okay, I want to point out now that writing moments in terms of these kappas also tells us quite something very explicit about freeness itself. And this can be seen if we make a multivariate version of this limit theorem. So instead of looking just on realizing one variable as the limit of sums of many small independent things, we should look at two at the same time. And then maybe we assume freeness between the variables, so we assume also freeness in the limit, and then we should see what kind of formulas do we get there. So that's essentially looking not just on moments of one variable, but looking on moments, joint moments of several variables. Or free variables. And I mean, what we really want to understand is how can we express in a nice way joint moments of free variables. I mean, that was still the goal. That we want to get a better understanding. How do we calculate these moments? And I'm saying that somehow these limit theorems give us a clue. So namely, I mean, writing one variable as a sum of many terms in the limit gives us some nice way of expressing the moment. And now we want to see what happens if we have two of them. So assume we have now those sums, but I have now two of them, so I put another index here, so this is the 1, so this is my first variable, so I'm summing n variables, and I assume that they converge to A1. So I make here the assumptions those guys classical, let's say free. No? Let's say we do a free case. So they are freely independent, and I mean each of them that are moment of this in the limit times n times this in the limit gives me some kappa. No? Okay, so I'm assuming here that phi of a n I of this first variable, we have power. This is some kappa, but now this kappa also depends on this variable, and it scales like 1 over n. No? So this was our limit theorem. Okay, so either we can assume n times this in the limit is this, or maybe we could also assume directly that it is this. But now I assume I have a second variable for which I have the same. So I also have an plus an. But now those are other variables, so they get index 2. And they should go to A2. And for those, I also assume that they are given in terms of those kappas. So I have here A and I2 is variable. We have the moment of this. This should be kappa R, but this is now indexed by the super index 2, also over A. Okay, so our limit theorem tells us that this assumptions. This here in the limit is given by summing over non-cross interpretations, and we get contributions in terms of the kappa 1s. And here we have the same. Okay, but now, so this is as before, but now I also assume that I know something about the relation between those two guys. If I want to look on joint moments, I should know, of course, if I want to look at joint moments in the limit, I should know what is the joint moments between this. And there I assume those guys are free. Because I mean, freeness between A1 and A2 is something which I want to understand. So, in addition, we assume that all those A's from here, for the first variable, they are free from the A's for the second variable. Also, I assume that the AN1s up to ANNs for the first variable, they are free from the corresponding AN1s up to ANN for the second variable. So those guys are free. And this should be true for all A. Okay. We only compare things for the same A. Okay, and I mean the freeness between those guys assumes that in the limit we also have freeness between these. This was one of the assignments which we did last time, that if I have sums, or that if I have variables which converge to something, and the variables themselves, they are free, that in the limit this freeness survives. So I mean here we have those guys are free among themselves, so this sum is free from this sum. Okay, I mean this sequence here converges to this thing, and this means in the limit A1 is also free from A2. So this means we can realize somehow the situation A1 being free from A2 by writing them in such terms as sums and assuming that those guys are free. And now we can try to imitate or to see how to calculate joint moments in terms of these A's, in terms of this guys here, which gives us a formula in terms of the kappas. And then we should check what happens, I mean, with terms where we have mixed moments, the A's, A1 and A2. Okay. Good, so the main thing here, what we get here, so this is by assignment, this was assignment 3, exercise 4. This means that A1 and A2 are also free. Okay. And this means we can try to calculate the joint moment in A1 and A2 as the limit of joint moments in those guys. And hopefully the calculation there will show us some more structure. This really needs to be the case. Okay, so in principle we should repeat the calculation which we did in our general limit theorem, but now not just looking on a moment of A1 or a moment of A2, but looking on a mixed moment, A1 and A2. Good, so let us try to do this calculation. So let's say we want to calculate a moment in A1 and A2, let's say a K moment, but we are multiplying some A1s with some A2s. So I'm fixing K, this is the number of factors which I want to have, and then I'm fixing a K couple of indices, whether I will have A1 or A2. So let me call them P1 and Pk. So multi-index. But they just take on the values 1 or 2. Of course, I could generalize this to more of them. Let's say we just have 2 of them. Okay. And then we have, so what I want is to calculate the moment A P1 up to A Pk. So this is a product of A1 and A2s in some order which is given or which is determined by the p's. If all the p's are 1, then of course it's just the kth moment of A1. If all the p's are 2, then it's just the kth moment of A2. But of course there are many situations where I have mixed moments. Good. And we calculate this by calculating the limit. I mean we know that this is given by the limit of taking the corresponding sums. So this is the limit and going to infinity of phi. And now I mean the AP1 I replace by the corresponding sum of those guys. And the A1 is given by this sum, so the upper index is 1, and the A2, the upper index is 2. So what I have here is the sum of A and 1 plus A and N, and the variable P1. So the upper index is here P1. Then I multiply it with the same thing for the P2 and so on, up to the last one, which is A and 1 plus A and N. And this is the pkth variable, so the upper index here is pk. Okay. Good. Yeah, and now we do exactly the same as before. So namely, we multiply this out, and of course then we multiply here, we get a product of k factors, and we multiply here each of the 1 up to n, the first term, with and so on, all the 1 up to n in the last term, which can be written as a multi-index. So limit infinity, and now I'm summing over all the possibilities for what I multiply here from each of the factors. And so this is a multi-index from k to n. And here I have phi of, I have here a n. From the first term I take I1. And the upper index is always P1. P1 here has nothing to do with the choice here, because I always have P1 here. Okay, then the next term is A and I2 for the variable P2 and so on, up to A, N, and the last I and K makes here the choice 1 up to N. Okay, and the upper index is always Pk, independent of the choice of Pk. Okay, so we get this. And then, as before, this is now a mixed moment in 3 variables, and we know that this factorizes, the value of this only depends on the kernel of this multi-index I. And then we know that such a product factorizes into products of moments of the corresponding variables, and we have to see what remains in the limit. So we know that this here is given by the sum over partitions of k. Okay. And then for each multi-index I, which has the same partition, we get here the same contribution. And this contribution we denote, let's say, by Gn of pi. But now, of course, it also depends on the upper indices P1 up to Pk. count how many multi-indices do I have, which have pi as its kernel, and this is at least asymptotically n to the number of blocks. More precisely, it's n times n minus 1 and so on. Yeah, but in principle, asymptotically, if n goes to infinity, what we have here is n to the number of blocks in pi. And the point in the limit was, I mean, if I ignore this, I'm just back to what I did in my limit theorem, that actually I have here n for each block of pi, and so this means this term here should better be only a product of number of blocks many variables. Because by our assumption, each moment scales like 1 over n. So whenever I have a moment of my original case, then it goes like 1 over n. Okay, and this 1 over n must be compensated by this n, which means here, what survives in the limit are only contributions where I have a number of blocks, many moments. Okay, and this in the free case, of course, means that the crossing partitions are also pressed. So this means here. So this means that we are still doing more or less the same, or exactly the same as before. I'm just ignoring the fact that I have also here indices P1 to Pk. Maybe let me just write this again as an equality. Also, I'm bringing the limit inside the sum. So this is the sum over partitions. And then I have the limit n going to infinity, n times the number of blocks of pi times gn p1 pk of pi. Good. Okay, so what are the surviving terms? If n goes to infinity, yeah, it depends how this factorizes. I mean, if a priori we have seen before that if I have a non-crossing partition pi, then this factorizes into products, exactly one for each block, and then in principle it's okay. If I take crossing partitions, then I get a factorization into more terms than I have blocks. So I will get here more 1 over n factors than I have here n factors. So those guys will disappear. So the surviving terms as before are the pi's which are non-crossing partitions. Okay, but so what is now? So this factorizes into a product where the lower indices are the same. So they combine the same lower indices. But now I have upper indices, and so I have now my blocks of pi, let's say. But now, I mean, I might have here a n, let's say 2, a n 2. Let's say here I have a n 7. Let me just write down. Forget the n. So here I have 2, 2, a2. Let's say here I have a7, a7, a9, a9. Those are the n, small n variables. Okay, this would factorize now into the product of, so this factorizes here into the phi of a2, 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 times the phi of a7, a7, and phi of a9, a9. Good, but now I also have upper indices. I mean, it could now be that all the variables which I have here are, let's say, the first variable. Then I would have here 1, 1, 1. And then this would just be a moment of the variable of those variables 1, and it would go like 1 over n. That would be nice. That would be okay. Good. Okay. But it can also be that, I mean, I have here variables for which I have an upper variable 1 and an upper variable 2. So this is coming from that I'm looking in my original moment, I'm looking here on A1 and here on A2. Okay, and then you see what I have here is the A1 and A2. But now the 1 and the 2 variables are also free among themselves, so I still have here a product in 3 variables, and this factorizes now further. Because this factorizes now into a product of this and a product of this. And so this means if whenever I have here a partition where I have a block which connects the 1 variable with the 2 variable, so where there's something 1s and something 2s appear in this block, then because the 1s and the 2s are free, this factorizes further. But each of them factorizes further into moments which behave like 1 over n. That's the assumption on our input moments. Okay, it factorizes into terms which go like 1 over n, but for this block I only have one factor n which can compensate it. So this means this would give you 1 over n squared, and this multiplied with n goes to 0. So I have to give a factor n to each of the blocks appearing here in the kernel I, which is my pi, but then better those blocks should not factorize any further, which means I cannot have a mixture of the 2 variables in this block. So this means what I see here is that actually I get some more pi's which don't contribute, namely those pi's which have blocks which connect the 1 variable with the 2 variable. And it's good that this disappears because I haven't made any assumption on the joint moments between this. Because if this would contribute, it would contribute with a mixed moment in those guys. But you see, I haven't made any assumptions about this. But I don't need, because whatever they are, they disappear in the loop. Good. Okay, so this means, in the end, that what we get here is more or less the same formula as before, namely that if I calculate the mixed moment AP1 up to pk, I'm summing over non-crossing partitions. I'm looking on free kings, but some of them will also disappear, and what I mean is that pi is less than the kernel of p. And with this I mean that this p here must be constant on the blocks of pi. For pi is not connecting variables, and A1 is an A2. You can only, for each block of pi, all the variables it connects must be either all A1s or all A2s. But it cannot be that some of them are A1 and some of them are A2. So this means that p's must be constant in each block of pi. Okay. In the next section we will make all this more rigorous. So we will really define this as order, but at the moment I think it's clear what it means. Okay, and so the pi's which have this property that they are not connecting in 1 with A2, they make a contribution, and the contribution is the same as before. So namely it's a product over the blocks of pi. And what is the contribution of a block of pi? I take the kappa. But now of course I have 2 kappas. I have one for the first variable, I have one for the second variable, but now a block connects one of the variables. And of course I take the corresponding kappa. So I take here the kappa. The sub-index is just the number of blocks, the number of elements in the blocks. But that I take here 1 or 2, this depends on the value of p restricted to this block. And this value is either 1 or 2. Of course, p must be constant on each block. Some blocks is 1, some blocks is 2. And so you see, we get here a very nice description somehow for the mixed moments, joint moments in several free variables in this summation formula, and there you see that that the relation between the variable 1 and 2 is they are never coupled in this formula. So we have here kappas only for the first variable and for the second variable, but we don't have mixed kappas. In this formula, the mixing disappears. So So in a sense, the cuppas will be, later we will call them free cumulants, cumulants. So on the level of the moments, the mixed moments are maybe not so easy to understand, but in terms of the cuppas, they are easy to understand. Namely, freeness just means that mixed cumulants are vanishing. Okay, I mean, this limit theorem more or less shows this to us. So maybe I want to write this down formally, what essentially we observed here. But then, of course, in the next chapter, we will investigate and develop this theory more. Rigorously. Okay, so let me write down the conclusion of what we have just calculated. Theorem. Good. Okay, so let A phi be a non-commutative space. If we consider two random variables, consider A1 and A2, which we assume they are either classically or freely independent. Again, we do it in parallel, classically or freely independent. Good. Okay, and now, yeah, we are saying that if I, in this context before, and this means that the moments of A1 written in this form where I'm summing over partitions. So I write the kth moment of A1 as the sum over pi, which is in the classical case running over all partitions, in the free case running over non-crossing ones. The contribution in any case is the same, meaning this is rolled over blocks of numbers, sub-index V, and I have here super-index 1 to indicate that this is for the variable 1. So I assume I have this for some numbers R1 and C. Well, we have seen that in our limit theorem we get such a writing, and we assume that the moments of A2 are given in the same form just for some other numbers. Okay, so then let me write down this we see here. And the moments of 2 are written in the same form, so then 5 k moment of A2 is given by summing over partitions, either all partitions in classical case or the free non-crossing partitions in the free case, and the contribution is again the product over blocks in pi. And the contribution of each block is just the product of the kappas corresponding to this variable, and the index is a number of elements in the block for some complex numbers. Good. Okay, so that's the input. So we assume I have free variables, A1 and A2 are free, and the moments for each of them is written in this form where I'm summing over non-crossing partitions. And then what we saw from this calculation, then we get more or less for free also the same formula for the mixed moments in A1 and A2. So the freeness has now the effect that the mixed moments have more or less the same formula. And then join moments of A1 and A2 P1, the last one is Pk. So I take AP1 up to Pk, and then this mixed moment is the same structure. It's given by summing over all partitions in the classical case, or non-crossing partitions, the free case. But now I have this extra condition that this partition should not connect in A1 with A2. So for each block, it only should connect either A1s or it should only connect A2s. But I'm not considering blocks where different 1 and 2s are connected. So I'm writing this that this partition must be smaller than this partition, which means that on each block of pi, this multi-index is constant. Right? It's either 1 there or either 2. But it's not on some of the i's it's 1 or on some it's 2. Okay, and this means for each block, we know exactly which cover we should take. If I would have a block which has some 1s and some 2s, I wouldn't know. There wouldn't be a cover which I should take for this contribution. But with this property, I can take exactly the same formula as before. So then the contribution of such a pi is the product over the blocks of pi. And then I take the product of the covers. And which cover do I take? Of course, exactly the one which tells me the pi on this block, the p. The p is constant on this block. So here I take the p on this block. So if I have a block which contains only the variables a1s, then I can take the kappa 1. If I have a block which only has the variables a2, I take the kappa 2, and I don't have blocks which contains both a1 and a2. Good. Okay. So you see, we get here somehow quite kind of structural formula for the mixed moments. So this is somehow the first understanding of the mixed moments in free variables. But it means it's not a formula which tells you directly how such a mixed moment factorizes, but it tells you get a nice formula if you write your moments in such a form, in terms of some other quantities, which we call cumulants, and also moments of A2 in this form, and then you can also write the mixed moments in the A's. Okay, and this will be formalized in the next lesson. But maybe let me just do an example and make the final conclusion what we have observed here, which will then be a motivation for doing a more rigorous and formal approach to those.
In our calculation, we use that the A1 and A2 are approximated by these sequences of either free variables. Is it clear that we can always do that?
No, this is again the problem. How do I realize variables? So we would have to go back to the formula, but you would have essentially we have to see that the kappas are uniquely determined by such formulas, and that's what we will do next time. Yeah. So, but modulo this effect, and again, of course, I should also be able to realize all these little AN1s and AN2s freely in some bigger space. So it's all these questions which we have not really addressed. But all those have a straightforward solution, and it's true. So in principle, this here is a proof. We have more or less given the proof. Modulo this question, you really can find kappas such that we can write it like this and that we get it in the limit theorem. But if you look at this formula, you will see that this is possible. If you only talk about linear functions, if you want positivity, then you have problems with this. On the linear level, finding those kappas is no problem. If you want to find such kappas such that you have positivity, then this is the context of infinitely divisible distributions. It's not really necessary for this channel. Okay. Good. Okay, so let me do just example, writing down maybe the structure of this contribution clearly, so that we are sure that we understand what I mean with this. So let's say in the free case, how do we calculate a mixed moment, let's say phi of A1, A2, A1, A2. Oh, okay, so what does this formula tell us for this situation? It tells us we should sum over non-crossing partitions of 4 elements, but only take those which only connect A1 with A1 or A2 with A2. Oh, so we can take this one, we can take this one, and we can take this one. Okay, of course there are more partitions, but they would connect A1 with A2. No? So I mean, I cannot take one which has a block like this, because this would connect A1 with A2. No? So we only sum over those 3 partitions, and then what is the contribution of them? I mean, each of them is a product of kappas, and for the first one, so I take this block here, this is a kappa 2, and this has the variable 1, so this is a kappa 2, 1. No? Here I have a block of size 1 for the variable 2, and here I have another block of size 1 for the variable 2. Okay, then the next contribution, so this would be this term. Here I have a block of size 1 for the variable 1. Then I have a block of size 2 for the variable 2. And here I have a block of size 1 for the variable 1. Okay, and then the last term, I just have 4 blocks of size 1 for the various variables. So a block of size 1 for 1, block of size 1 for 2, block of size 1 for 1, and a block of size 1 for 2. Okay, so that would be the classical way of writing. If A1 and A2, no, this is a free case. If A1 and A2 are free, then we get this formula. And in the classical case, of course, the formula is different because there are more contributions. We have an additional term, which is a crossing contribution. Because I mean, I can, of course, also connect this with this and this with this. Of course, this is a crossing contribution. This doesn't show up in the free formula, but it shows up in the classical formula. So there we would have an additional contribution, which would be kappa, a block of size 2 for the variable 1, times a kappa for a block of size 2 for the variable 2. Okay. So I hope the structure of the formula is clear, but next time, in the next chapter, we will really go much more into this. But so maybe here I end with the conclusion which we draw from all this, namely that it seems to be good to write moments of our variables in such a form where we sum over all or non-crossing partitions and we write things in a multiplicative way, because freeness somehow is reflected there that we don't have we should not cross for the kappas. We should not connect 1 and 2s. Okay, so the conclusion is, so if you write moments of our variables as sums over non-crossing partitions, so that's restricted to free case, and this sum in a multiplicative structure. So I mean each term there is a product, so we write it multiplicatively in terms of quantities which we call kappas. Then the freeness of our variables can be described quite nicely, also in terms of such formulas. Then freeness of the variables having in joint moments no mixed kappas. So this means no blocks which connect different variables. Okay, so in our moments, of course, we have joint moments. We want moments which are mixing A1s and A2s. But if I'm writing it in terms of the sum over numbers and partitions, then here I will get kappas which are not mixing the A1 and A2. So on the level of the kappas, freeness is somehow quite easy to describe. It seems to correspond to the vanishing of all mixed kappas. Okay, so I mean these kappas will become very important for describing the structure of those formulas, and so we should make a more rigorous theory of this. And so in particular, I mean the kappas will be called the free cumulants of our variables. So in contrast, so we have up to now we have looked on moments. We want to understand moments, but this here tells us maybe for understanding moments, it's good to go over to kappas, which are somehow defined by relations like this. Okay, and then you can describe many things much nicer in terms of the kappas. Okay, but this is, I think, enough for today. But next time we will start a more rigorous investigation of how really to define the kappas, and that maybe we really have this property that freeness corresponds to the vanishing of exponents. Good, that's it.